Welcome, everyone. I'm Lauren Ross, the Manager of Engineering and Research at the American Wood Council, and I serve on multiple ASHRAE committees, both for residential and commercial. And we're going to be talking today about meeting residential energy requirements with wood frame construction, specifically for the 2012 IECC. This presentation is copyrighted. Here's some AIA information about this presentation. Here's our first polling question. You'll note that this is typical for our polling questions. It's more to gather information about you and what you think than anything else. It's not going to affect your participation score in any way, shape, or form.
All right, go ahead and vote. Many of you have already started. I usually give you about maybe 30 seconds to a minute to finish these, or 80%. This one's very, very easy. So go ahead, and I'm going to go ahead and close it, and then I'll share the answers. All right, so we've got about 50% engineers, 32% code officials, 11% architects, and just a smattering of building designers and others. So.
Oh, good. I'm glad to see that there's some code officials out there. That hopefully this will be beneficial for them too. Okay, these are the learning objectives as stated in the description. But this is basically the outline just that follows right from the learning objective. So we're going to start very simple with R values and U factors. What are they? How to go from one to the other. And then we're going to talk about the compliance paths within the IRC and IECC and what trade-offs there are in that. Throughout the presentation, we'll be doing some example problems and talking about design aids the AWC has for doing these problems. And at the end, if we have time, we'll take some questions. Okay. So, jumping right in, R value versus U factor. So an R value is the measure of resistance to heat flow. So it's literally measuring the resistance. Okay. And it's material or product specific. So like in this picture right here, this product is showing an R30 resistance, okay? And that's usually what you're typically used to seeing is a band of insulation with a certain R value. But materials have resistances too. For example, wood has a typical resistance of 1.25 R per inch of thickness. And they're either labeled on the product or they're in the ASHRAE Handbook of Fundamentals. What's nice about the R value is it can be summed. Resistances can be summed. So if I put one insulation layer on top of another insulation layer, those R values get summed up. So since the heat has to flow through one resistance to another resistance, it's an additive effect. U factor is kind of the inverse of the R value. It's a measure of the heat flow, so it's how much heat flows through it. And it's more assembly specific. So you might be used to seeing it on like a window. So a window will have a U factor of, for example, in this case, 0.35. Now that is for the assembly of the window. Okay. And they're also often used for assemblies of entire walls or floors or something like that. And they're derived from the sum of R values. And you can't just sum U values as easily as you can R values. They're more area weighted averages than R values are. Okay? So for doing wood construction, we use what's called the parallel path method. There are other methods that can be used that are more complex, but since wood itself is a fairly decent insulator material, you're allowed to use the parallel path method according to ASHRAE Handbook of Fundamentals. So when you're trying to convert R values to U factors to try to get the U factor for this entire assembly, for this wall, for example, what you do is you get the R value for all the different components. So we have an air film, which is kind of the outside air film, and then we have, or this one's the inside, and then gypsum, stud, insulation, OSB, vinyl siding, and another air film. And we say, what path is it in? Because some of the heat is going to go through the stud, and some of the heat is going to go through the cavity or the insulation. And what you do is you say, okay, I sum the R values in each of those paths. So for the stud path, I sum up all the ones that the heat would have to go through. So it doesn't go through the insulation, but it does go through the stud, and its R value sum is just about R7. For the cavity, it doesn't go through the stud, but it does go through the insulation. So its R value sum is about 15.6, okay? And then I find the U factor for that path. Now the U factor for that path is just the inverse of the summed R value. So 6.995 inverted is 0.143. 15.62 is 0.064. Now what I'm going to do with that is I can't just add those U factors. That's the heat flow through each one of those paths. I have to say how much area is stud or wood, how much area is that wood path, and how much area is the cavity path. And that gets what's into called the framing factor. Okay? So here we have a wall. The framing factor by definition is the projected area of wood divided by the total projected opaque area of the wall. So it's just the opaque area. So all these windows and things like that, they don't count in the denominator. Okay? Now, a framing factor is based largely upon a study that ASHRAE did that surveyed typical construction. And they found that headers come up with to be about 3 to 4%. If you're doing studs 16 inches on center, they're 21 to 22%. Studs 24 inches on center, 18 to 19%. So if you add say headers plus studs 16 inches on center, you come up with the default framing factor of 25%, and that's pretty standard for what you use. If you use studs at 24 inches on center, you come up with a default framing factor of about 22%. And that's, again, another pretty standard number that's used. So here's another poll question. This is more to see if you're paying attention than anything else. What is the definition of framing factor?
All right, so is it projected wood area, projected wall, opaque wall area, or B, projected wood area, total wall area, or C, 25% for all buildings, or D, other?
Yeah, so that's projected wall area divided by projected opaque wall area is A. B, projected wood area divided by total wall area. C, 25% for all buildings, or D, something else, other.
All right, I'm going to give you about 10 more seconds. And I'm going to close. And we've got about 69% say A, projected wood area divided by projected opaque wall area. 28% say projected wood area divided by total wall area, and just a smattering for the other two answers. All right, and okay. Lauren, tell us what the real answer is, please.
So the real answer, according to ASHRAE, is A, because it's only about the opaque wall area. That's all they care about. If you do a ResNet or HERS index, something along those lines, then your definition is B. There's a difference between how ASHRAE defines it and how HERS defines it, or ResNet defines it. And that's the difference, is between A and B. And C is a fairly decent answer in that that's kind of your default value if you're using 16-inch on center studs. So truth is all the answers are okay, but the answer I was hoping that you would guess was A, because that's how I emphasized it in this presentation. Okay, so going back to our example, okay, so we have the U factors for going through the stud path, and we have U factors going through the cavity path, okay? And from the framing factor, we're just going to assume it's 25%, okay? 16 inches on center, normal headers. So we say, look, 25% is going through the studs, 75% is going through the cavity. We just take the U factor of the studs, multiply it by 0.25, or 25%, add then the 0.064 and multiply that by 0.75. 75% is going through the cavity. And we add those two together and we get an overall U factor of the assembly, 0.084. Okay, so there's certain numbers that I'd like you guys to remember during this presentation, and this is one of them, 0.084. So this was a R13 wall with 2x4 studs, okay? 2x4 studs, R13 wall, and that has a U factor of 0.084, okay? So remember 0.084 for me during the presentation. We'll come back to it, okay? There's just showing the math right there of how we got to 0.4. Wouldn't it be nice if you didn't have to do all that math? That's one of the design aids that we came up with. This is a table out of DCA 7. And this is showing, hey, look, wood 16 inches on center with interior sheathing, exterior sheathing, and look, if you're using vinyl siding, 2x4 R13, look, there's our 0.084. It just gives it to you. So you don't have to do all the calculations. And that's one of the design aids that we have. And we'll talk more about DCA 7 in a bit. But we wanted to give you something that made it so that you don't have to do the calculations. So now we're talking about the compliance paths. Now the same options are in the IRC and the IECC, okay? They were made to align in the 2012 version. This was kind of new to the 2012 version, and it will continue, as I foresee, it will continue to go that way. They made it so that there's really no distinction between the two. And so when we're talking about, if I say IECC, it's just as applicable for the IRC. So whatever energy provisions your local jurisdiction's adopting, or whatever it may be, then those are it. So we're talking either Part 4 energy conservation of the IRC or the residential provisions of IECC chapters 1 through 5. Okay. There's 3 prescriptive compliance paths. There's also a performance path, but that requires more intense modeling, and so it's kind of outside the scope of this presentation. But the 3 prescriptive paths are the R value path, which is very simple, and it's cavity or cavity and continuous insulation focus. So just as long as you have enough insulation in there, you're fine. It just says, I don't care about anything else, just put enough insulation in. It's the least flexible though. If you do anything that's out of the ordinary, you're stuck. You probably can't use that table. The U factor method is similar to the R value in that it's a table-based methodology. So, but it's assembly-based, so it's a performance-based. It says, look, your assembly has to meet this requirement. Instead of saying your insulation has to meet the requirement, it's the overall assembly of the wall or the roof or whatever it is has to perform at this. So you can trade off parts within the assembly. If you're using like a structural insulated panel, this might be a good way to go, because it's not going to be in the R value table for a structurally insulated panel, but your overall assembly might be equal to or better than whatever is in the R value table, and so you can say, look, through U factor, I'm equivalent. The total UA methodology is the most complex of the prescriptive paths. It allows trade-offs between assemblies. So it says, look, I don't need to have quite as good of walls if I beef up my roof, for example. And it's the method that's used by DCA7 and ResCheck. And we'll talk about those both in a little bit. But it's the most complex and most flexible of all the prescriptive methods. So the R value compliance path. It's pretty straightforward. All you have to do is know your climate zone when there's a map at the beginning of the IECC, and it has the counties and things on it. And so you pick out your climate zone, and then, for example, your wood, if you're doing a wall, you just say, look, this is how much insulation I need. So for our example, that was the R13 2x4 wall, it's compliant in climate zones 1 and 2. Now you'll notice that it doesn't actually say whether you need a 2x4 or 2x6 on there. It's just kind of an assumed information there that you're not going to try to put R20 into a 2x4. Okay. You'll also notice that the fenestrations are labeled in U factors because they're assembly, and that there's no requirement in climate zone 1. Okay. Also, in these R value tables, that's this famous footnote H. Okay, this is the 2012 IECC, and there's footnote H is literally what's just on the screen right there, but there's two parts to footnote H. Okay, the first one describes what it means if it says like 13 plus 5 or 20 plus 5 or 13 plus 10. The first part, the 13 or the 20, is the cavity insulation. So that's the bat insulation or whatever. It's the cavity part. The plus whatever is the continuous insulation that's on the outside or wherever you put it. Okay, so that's the first part of footnote H. The second part of footnote H is this: if structural sheathing covers 40% or less of the exterior, continuous insulation R value shall be permitted to be reduced by no more than R3 in locations where structural sheathing is used to maintain a consistent total sheathing thickness. So you're actually allowed to decrease the continuous insulation a little bit if you've got some structural sheathing to make it so you get a nice flush wall. Now that second part was actually moved into the main text in the 2015 IECC, but it's still there. So the U factor path, this is the main table for the U factor path. It's pretty similar to the R value path. You get your climate zone, and then you say, look, this is what I need for my wall, for example. Okay? So then you have to do your calculation for your U value and check it out. So what this basically says is, look, if I have two different walls, this is my base wall, and if I have two different walls, say I'm using insulated siding or whatever it is, and as long as it's equivalent, it's okay. It's the energy performance. Okay, as long as it has the same U factor, I'm okay. And you'll also notice that the fenestration values are a little bit different in this one because we've got a 0.5 U factor in climate zone 1. And that's because for the U factor table is also used in the UA alternative method and for the performance method. So they had to give a value here for what the base assumptions are. Now, here's kind of an interesting thing with the 2012 IECC. If you notice, we said in the R value table that an R13 wall would work. And we calculated in our first example that U factor was 0.084. But now we look at the frame walls, and they require a 0.082. Now, U factors are maximums because they're the amount of heat flow that can go through with the assembly. So since our calculated value of 0.084 is larger than 0.082, it's non-compliant. It doesn't work. So we were allowed in the R value tables, but if you did the calculations for the U factor tables, it doesn't work. Which brings us to the next poll question, which is kind of more of, I'm interested in what you're saying. So, is a 2x4 wall, R13 wall, compliant in climate zones 1 and 2 with the 2012 IECC?
Okay, so your choices are A, yes, but only using the R value path, or B, no, its U factor is too high, C, whatever ResCheck says, or D, all of the above. Go ahead and vote. About 15 more seconds. And I'm going to go ahead and close the poll and share it. All right, so about 50% say yes, but only using the R value path. 20% say no, the U factor is too high. 28% say all of the above, and just a couple say whatever ResCheck says. And Lauren?
Yeah, this one's kind of a hard one to answer because they're all kind of right in what they do, and it's really based upon the assumptions that you make, and because of this ambiguity, us and several others went into the 2015 to try to resolve this issue, to try to align the R values and U factor table, and we're successful in doing so to make it so that it aligns so that there's not this discrepancy between the R values and U factors. Now, there still might be a couple, and it still might be in some places, but it's not near as bad as it once was. Okay. The total UA alternative. This is the language of the total UA alternative path. Basically, the idea is in the U factor table, it allows a certain amount of heat release in any given assembly. Okay, so much goes through your roof, so much goes through your fenestration, so much goes through your wall. Okay, the UA table, or UA total UA alternative, basically says we don't care what those percentages are, just as long as the total amount of energy that your house loses stays the same. So if I reduce the amount of energy that's lost through my windows, I can increase the amount of energy that's lost through my walls, or vice versa, or what other parts of the assembly components of the house. So as long as the total UA, which is U, which being the energy loss per square foot, times the A, being the area of that loss, remains constant for the entire house, you're okay. So this is in an equation form for those engineers like myself among us. So U reference, basically meaning the reference from the table, the U factor table, times the area of the assembly, which is your proposed house, and equals the U actual, your proposed U value, times the assembly area. And since the A assemblies are going to be equal, you're just basically trading off one U for another U. So we'll do an example here in a little bit. But first, let's talk about what trade-off options might be good for us. Okay, so you look at the fenestration U factors, right? They're 0.5, 0.3, right? They're pretty high, especially in comparison to, say, like the wall values. They're almost an order of magnitude higher than the wall values. This means that a slight trade-off or slight benefit improvement in the fenestrations can make a large difference in the walls, because there's such a huge difference in the U factors. When I'm saying what am I saying when I say a slight difference in the fenestration U factors? Okay, so let's talk about Energy Star. Okay, so this is some of the Energy Star information that was out there, and this is kind of their U factor requirements. Okay, so climate zone 3, the U factor table says I need a 0.35 fenestration and a 0.057 wall. Okay. Energy Star said I need a 0.3 fenestration. Okay, so if I use a Energy Star window in my house, I'm changing the fenestration from 0.35 to 0.3, and we'll look in our example what that does to this requirement of a 0.057 wall. Okay, so this is our example. It's a real simple 30 by 40 two-story house with 16% window area. When I say 16% window area, I'm talking 16% of the exterior walls are windows. Okay, so the total wall area, both windows and opaque walls, is 30 times 8. We'll say it's 8 feet high, times 2 because there's a front and a back, and times 2 because there's 2 stories. And similarly for the 40-foot side, right? Which gives us 2,240 square feet. Okay, and 16% of that is window, and that leaves 84% of that is opaque. So we've got a window area of about 360 feet and an opaque wall area of about 1,880 square feet. Okay, so this is the reference UA. So this is right out of the table. Okay, this basically is how much UA can I use. So we get that window area times the 3.5, which is from the table, saying, look, this is the maximum you could use, which is 125. Now I'm dropping the units because it doesn't really matter, and they're kind of ugly. And then the opaque UA, which is the opaque area times the maximum U allowed in the table, which comes out to 107. Now you'll notice that these numbers are pretty close to each other, 125 and 107. So even though there's a lot more opaque wall, because of the difference in the U factors and in the efficiency of the thermal efficiency between the opaque and the window, makes it so that almost the same amount of energy is released between the 16% area of window and the 84% area of wall. Okay, so that comes to a total UA for my proposed home of adding those two together of 232. Okay, so here's my proposed home now. Okay, so that was the reference. That was using the 3.5 window. So now, if I use a 0.3 window, I multiply the window area by 0.3, and I come up with a UA of 107. Okay, I subtract 232, my total allowed UA, minus the 107, which means that I have 125 to use for the opaque area. Okay, so that's my opaque UA. And I find its new U value just by taking its UA divided by A, and that gives me its U. So 125 divided by 1880 gives me 0.0665. So in essence, I've changed that 0.057 into a 0.0665 just by going to an Energy Star window. Okay. This is the next number that I want you to remember in this presentation, is this 232. Okay, that's going to be important to remember coming along. Okay, but also remember that I've changed the value to a 0.0665. Okay, so what does changing to a 0.0665 wall actually do? Okay, so here's again another table for walls saying This is the U factors for them. And if we look, what does a 0.057 wall look like? Okay, so if I have 2x6 studs with R19 insulation, I can make, and I have an R2 insulated vinyl siding, I can make that 0.057. Okay, but now I've used an improved window and I can get to 0.0665. Now what are my wall options? Okay, I can trade off and say, look, I don't need the insulated siding anymore, so I can make this without any problem. 0.063. I'm even better than that, than the 665. So just by having a little bit better windows, I no longer need insulated siding. If I have a brick veneer or something along those lines, I can even go down to R15 cavity insulation if I wanted. To show that this works, here's ResCheck. Okay, so this is putting in the information we had. So it shows the gross wall area that we calculated, the window area that we calculated, the U factor that the wall was, the window that the wall was, and it says it passes. Okay, and it says it's 0% better than code because we are trading off 1-to-1. Okay, and you can even see the compliance methodology is UA trade-off, max UA 232. There's that 232 that we calculated as our allowed UA, your UA 232. So that is ResCheck doing it. So ResCheck doesn't, it allows the trade-off, but it doesn't tell you what the trade-off, it doesn't leverage the trade-off for you. It says you can do it, but you would be entering in this number and guessing and checking. Okay? Wouldn't it be nice if you had a design for code acceptance that did all those calculations for you? That's what DCA 7 is. So that's the design aid that we've got. It has background on compliance paths, just like we went over in this presentation. It has U factor calculations, just like we went over in this presentation. It has U factors for various assemblies in Appendix A, which are those tables that I was showing you. And it's got them for OSB, plywood, fiberboard, studs at 16 inches on center, 24 inches on center, 2x4 studs, 2x6 studs, and cavity installations R13 through R24. Okay? And then in Appendix B, it's got that UA trade-off for fenestrations and walls for the 2012 IECC. So let's talk about Appendix A in DCA 7 for a little bit. These hopefully look a little bit familiar since I've used them twice now. These are the tables that have the U factor calculations. So what you do is you say, look, what stud spacing am I at? You go in and say, I've got 16 inches on center stud. So right there at the top and right there, it says this table is for that. Okay? The one to the right is for 24 inches on center studs. And then what is my sheathing type? Both of these are wood structural panel sheathing. These two examples that I chose were wood structural panel sheathing, but there are others. Okay? And then you can say, okay, what stud size? In this case, I'm just picking 2x6. I could have gone with 2x4 just as easily. And then I say, what's my insulation? And what is my siding? I just go across. And boom, I have a U factor for that individual component. What's interesting about this is that I can actually compare with this. So if I look at the difference between the 16 inches on center and the 24 inches on center, I can look and the difference is about 0.002 of a U factor. And that's pretty typical from going from 16 inches on center to 24 inches on center, is 0.002 of a U factor. Okay? So let's talk a little bit more about the framing factor and U factor and how that works. Okay? So these are three very typical configurations in the IECC. A 2x4 with R13, a 2x4 with R13 plus 5, and a 2x6 with R20. And these are typical framing factors. So R25, our baseline, 16 inches on center. Framing factor 22, if we go to 24 inches on center. And the other ones are if we do insulated headers or raised headers or something fancy like that. So if you look, you can see that these are our baseline, our normal framing conditions, okay? But as we reduce the framing factor, as we have more cavity and less wood path, you improve the U factor. So we improve the U factor to 5/1000ths of a U factor. So I do a lot of work and I get 5/1000ths of a U factor. So if you only need a little bit of a U factor change, then changing your framing might make sense. If you need a big change, it's probably not worth it. Okay? Look at the one with continuous insulation on it. If I look at it, it starts out pretty good and doesn't make as large of a difference. That's because the difference between the cavity path and the wood path already is slightly mitigated by this continuous insulation. So the framing factor doesn't have as much to play into it. Another thing to note is that an R13+5 and a 2x6 R20 start off with the base being the same at 0.06. That's why in the IECC they are equivalent in the R value, or in the R value tables. They're either options. Okay. So moving on to Appendix B in DCA 7. These are where you have that trade-off between walls and fenestration values. Okay, so this is climate zone 3 because there's a table for each climate zone, and it lists right at the top what the reference values it's assuming are. So these are pulled right out of the U factor table. So again, 0.35 for windows, 0.057 for walls, just like we did in our example. Okay. And you look at the top, see climate zone reference values. You look at the top and it says percent fenestration in total wall area. So these are that percent fenestrations, okay? Along the side is the average U value for exterior walls, including the siding. So if you have to know the U value for your wall, which links back to Appendix A, which actually has the calculations. And then in the middle of the table is U factors for fenestrations. Okay, so this is how you can kind of read the table. So for our example, we had 16% fenestrations, right? And we were going to use a 0.3 window. So we go on down until the last time we see 0.3. And then we go over and we say, look, 0.057. So that works out the same as our calculation. We can also do the other way around. Say we know we want a certain wall type, okay? A certain wall type, and we know that we have a certain wall type, but we want to know how good of a fenestration we need, okay? So we have a percent fenestration area of 18%. We go down until we reach the wall we want, which is in this case 0.068, and we go across. And again, we need a 0.3 window. Okay, so you just go down and across. So it's basically the same reading. It's just going the opposite direction. And again, here's res check showing that the same thing can be done. The difference is res check, you'd have to guess and check to make sure that it works, whereas with the table, it does it for you. It shows that it works, so you don't have to figure it out. Well, we recognize that tables are annoying to read and aren't very fun. So we decided to make our own calculator, and it's still a little bit in the development process. We're going to make it for iOS, Android, and Silverlight. And the iOS and Android, they're still they're being updated and getting ready for the third-party process because that takes a little bit longer. But the Silverlight, or the PC version of it, is going to be free, and it's going to be posted on our website really soon. So if you go to our website, awc.org, there's this calculators button right here. And you just click on that, and it has several calculators, some of which are really handy, like the connections calculator and the span calculator and things like that. But among them will be this energy DCA7 calculator. Okay, and we just need to, we've got it finished. We just need to put it up on the web now. So this comes to the next polling question. How familiar are you with AWC's website?
All right, so have you never been there? Have you never been to our website? You've only gone there for education. You're familiar with publications and calculators, or maybe it's your home page. So go ahead and tell us how familiar you are with our web page. So.
And while I really hope it's your home page,
awesome. We actually have a couple people that say it's their home page.
That'd be great. It's not even my home page, so.
That is awesome. I am thrilled to see that. All right. Just a couple more seconds. And I'm going to go ahead and close. And share. All right, so the majority of you are familiar with publications and calculators. That's probably to be expected. And then 39% go for education. That's again probably to be expected. 5% of you have never been to our website. Please go check us out. And 3%, it's your homepage. That is awesome. Awesome, awesome.
There's lots of great stuff at AWC's website. We have a whole bunch of things, especially for code officials. There's a code connections area that is to keep you up to date with what's going on in our industry, and you can become a design professional member as well at our website. It has lots of great things on there, so I recommend everyone checking it out. So here's the example of the calculator itself. This is the PC version, because it's free and easy to use and everything. So I'll just show you kind of the buttons and things that go along with it. So first off, you pick your climate zone, just what you would expect. And I'm using a green box here because that's a required input. Okay, you have to have a climate zone, otherwise it doesn't know where you're even talking about. Then it will populate the required U value and required fenestration. Basically, what it's talking about is the U factors from the table, okay? And you can modify these if you want to. You don't have to, and I recommend not unless you know what you're doing. But if you have, say, a state-specific value, like if you're North Carolina or someplace that has a state-specific value that they've altered the IECC, they've amended it, then you can insert those. It'll give you a warning saying, look, this isn't what the generic IECC says, but you can proceed to go on with that, okay? The next is the percent fenestrations, because if you're doing that trade-off, that needs to know how much is that trade-off going to be, okay? Sheathing materials, this is just basically to limit how many options it actually shows over here on the right-hand screen. You can click on any of those and go back and forth between them, but we found that it was a little overwhelming if we showed all of them, so we kind of limited it down. This is the direction the calculation is going. If you need the wall, for example, then that means you know what your fenestration is, and you need to know what the wall value is. If you click on fenestrations, that means you know what wall you have, but you need to know what fenestration value would allow you to use that wall. Okay? So it's basically which direction in the calculation you're going. This right here is the actual, and it depends on what button you are picking, fenestration or wall value. So it's where you put in, I'm going to use this value for either my fenestration or my wall, and I want you to determine the other one, okay? And this is the output. So this says, in this case, this was our example, a climate zone 3, I'm using a 0.3 window, and I get I need a wall of 0.0665, okay? And then it gives you right here on the calculator, look, I can use 2x4s, 2x6, and it gives you what insulation values I need. Now you'll notice that some of these cells are highlighted in red. That's because a typical bat is not made for that level of, or that deep of a stud. It's hard to find an R27 bat to fit in a 2x4, for example. So it's warning you, saying, look, the user is kind of responsible to figure out if this makes sense or is reasonable for that type of thing. Okay, and these are performance value R values. So if it says R20, that means it needs an R20 after compression to be in that value, or to be in that cavity. So like this R19, I can't just stick in any old value and say, well, it might need an R20 that's compressed to make the R19 value. Okay. So this is going the other direction now. Okay, showing the other direction. So I clicked on fenestrations. And remember, I wanted to use a 0.068 wall, and again, it's showing the 0.3 fenestration value. What's cool about this is I picked what wall U factor I wanted, right? I said I want a 0.068 wall, and now it's giving me options of what can make that 0.068 wall. So it's a sneaky way of saying, how do I get a wall with a certain U factor? Okay. So that's one of the tricks that I like about it. So this is the future plans and desires for the calculator. So we're not done with it. We're still working on it, and we're hoping to get more stuff into it if we have time and things to do and ability to do it. Currently, the calculator is limited to the 2012 IECC. We recognize that the 2015 is out there, and in a lot of ways we like it better because it's a lot easier to use. So we'd like to make it so that the calculator is also has the 2015 IECC reference values. Currently, you can use the 2015 values, but you have to insert them. Whereas when I was talking about that state specific, you'd have to just insert them in that. Okay. State-specific reference values is along the same lines. So instead of having to insert them manually, you just drop down box and pick your county or whatever it would be, and it would populate your climate zone and your state values. That would be a really nice feature if we can eventually get it. Okay. The U-factor calculator is another part that we would like to do. So instead of having a table that says these are your components that make up a U-factor, we would like it so that you could say, I want to make a wall basically from scratch, and say, I'm going to use 2x4 studs, and I'm going to add this, and I'm going to add this, and I'm going to add this, and it, as you go, creates the U-factor. So you can come up with what is needed, or you can create your own instead of limited to what's in the tables. And lastly, a stretch goal would be to add moisture criteria. The Canadian Wood Council currently has a database of walls that are approved or work well in their climate zones. And that would be really nice to have criteria that says this is a wall that will work well in your climate zone or in your area. That would be really nice if we could add that feature to it, so it's not just energy but also a moisture issue. Okay. Okay, take-home messages from this thing. R values and U factors are related, but require some form of calculation to go from one to another. There are 3 prescriptive compliance paths in the IRC and IECC, but they trade off simplicity and flexibility. Modern energy codes have tightened, especially the opaque envelope requirements, but you can leverage the UA alternative method to alleviate some of those requirements. You can use it to make it so that it's not quite so painful. AWC has online aids for determining U factors and for using that UA alternative method at our website, awc.org. Okay. Any questions? How can I help you now? We've got about 10 minutes left, and I'd love to answer something.
All right. We've got a few questions that have come up, Lauren.
Mm-hmm.
All right. The first one is, if for the total UA method in ResCheck, what are the mandatory minimum requirements? Can the R values be lower than the prescriptive values?
So the mandatory minimums, how do I put this? So yes, the U values can be less than the mandatory. There is no real backstop per se in the total UA methodology. The closest thing they have is a backstop on the fenestrations, which says you cannot use really bad fenestrations. But as far as like the opaque portions of them, they really don't. They don't have a backstop saying you can only leverage it so far. Okay?
All right, cool. All right, our next question is, do you have wall assemblies which include the +5 continuous insulation?
Unfortunately, no. We don't have any of those yet included. That would be another area where we'd like to do some more to expand upon it. But we just don't have that at the moment.
Mm-hmm. All right, great. How about, here's another one. Where can you find climate zones in the IRC?
In the IRC, let's see. I think they're also in the IRC at the beginning, but I'm not sure. I more often use the IECC, which has them at the start of the residential and the commercial chapters. So I'm not as familiar with where they would be at in the IRC. It's really easy to find them online at like DOE and things like that, though, if you're unaware.
Great. All right. Next question. Can you show us the online calculator again and do a quick example with it?
Yeah. Let's see. So, okay, can you see the calculator now, Lori? Is that
Yep.
working out okay? Okay. So this is the online calculator right now. It's still working. So let's do a little bit stronger climate zone here. Let's do climate zone 6. So I just literally clicked on climate zone and then I picked 6, and it gave me an error message saying, hey, look, that my values were funny because I just picked a climate zone that was significantly more stringent than what I had, and so it adjusted it. So it kind of took care of that for me. And then let's do a higher fenestration percentage. Just go up to 20 this time, okay? And let's do OSB, and let's calculate the needed wall, okay? And then let's see. So this required wall is 0.048, 0.32, and let's do. I think I've got a 0.25 window at my house. Yeah. So again, this would come out with a wall U factor right there, 0.0655, and that's what it is, and it has the options. So again, in northern climate zones, it's pretty hard to get 2x4s to work sometimes. So oftentimes you'll end up with a 2x6. Okay.
Great, thanks. All right. During the presentation, you mentioned that a few things have changed between the 2012 and the 2015 IECC. What other significant changes can we expect?
Yeah, so the 2012 and the 2015 IECC, there were the biggest thrust for the difference between the 2012 and 2015 wasn't so much to change the stringency or change the amount of energy used in the actual code, but was to increase compliance and verification and ease of use. So I think DOE did a determination and found the residential was only like a percentage or two difference in actual energy use. But the goal was to be more flexible, more user-friendly. So a couple of things did change, like I mentioned, the U factors and the R values aligned a little bit better. But probably if I had to say the single biggest change was there's a new compliance path, which is known as the ERI path, or the Energy Rated Index path. What it does is it allows something like a HERS score to be used to show compliance for the IECC. But it should be noted that it does have a backstop that you can't go past. I think it's the 2009 IECC envelope provisions.
Okay, great. Another question, does the Energy UA calculator have 7/16 OSB?
Yeah, so the difference between like a 7/16 OSB and 3/8 OSB is practically none as far as the R value is concerned. So what you're looking at there is I mean, the answer is basically no. It's got what it's got, the 3/8. But for effective, how much is it really going to make a difference on your wall is very, very minimal. So it almost doesn't matter. Okay.
Okay, great. Another question here. You said the default framing factor is 25% for standard walls. Why does ResNet have it at 23%?
Okay, so that goes back to the difference in definition, right? So ASHRAE defines the framing factor as the projected wood area divided by the opaque wall area, whereas ResNet defines it as the projected wood area divided by the total wall area. So the denominator is different, with ResNet having a larger denominator because it's the gross, not the net, and so it's the same amount in the numerator. It's just the denominator's larger, so it goes down. They're actually talking about the same amount of wall. Okay. So it's kind of an apples and oranges little bit of thing.
And you mentioned that the IECC usually follows the ASHRAE convention.
Yes, yeah. More often than not, the IECC is going to follow the ASHRAE convention. I don't think the IECC talks too much about framing factors, but if you look at maybe the commentary or supporting documentation for it, more often than not, the IECC is going to follow ASHRAE convention, just because of how code has been written and goes forward with it.
All right, great. This question's a little more qualitative. What direction are the energy codes going? Obviously, you mentioned to our audience that you're on several different energy committees. What should we expect in the near future in terms of energy codes?
That's kind of it is an interesting question. I mean, my opinion is probably going to be different than other people's opinions, but I see energy codes more going towards flexibility, and yet at the same time more towards standardization. They're trying to say, look, we've gotten all these great results from energy codes. We've really tried to get good, efficient envelopes, good, efficient buildings, but now we need to make sure that we're actually getting the performance out of these requirements, which means that we need to have the way of verifying that that's what we're after, that the compliance is really there. And so that may mean more standardized forms of testing, like blower door tests and things like that have to follow a certain regulation. We might not have two definitions for framing factor in the future, or something along those lines, and it might be more standardized, so we're all talking the same language and doing the same thing, so that it's not as crazy and so that we can get it. One meeting I had they were talking about how it's not uncommon if you use 2 different energy programs to model the same house that you can get results differing by about 10%, and that's a large percentage. If you imagine doing a structural calculation and saying, oh, I'm off by 10%, that's kind of scary. So we need to make sure that we're getting more standard, reliable result from what it is, and I see that coming down a lot more.
All right, great. All right, well, that's I think that's all the time we've got for questions. I think we are going to send it over to Marcy now for a little bit of wrap up at the end and just a little bit of housekeeping to close things out for us.